This is SourceFlux, an information stream delivered via an audiovisual broadcast. There is a distinct possibility that our universe is nothing more than an enormous computer simulation. This notion is based on quantum chromodynamics, which is the idea that describes how the strong nuclear force binds quarks and gluons together into protons and neutrons and thus binds everything else together. These are very fundamental physics that describe the process by which elementary particles form larger particles, which form larger particles, which form life, the universe, and everything. Researchers have long sought to model quantum chromodynamics on supercomputers, but the problem is that these kinds of simulations take place at such a small scale and are so complicated that even the biggest supercomputers can only simulate an extremely small portion of our infinitely massive universe, something just a few femtometers across. A femtometer is 1 million nanometers. But, such a simulation is also so elementary, so very fundamental to the construction of the universe, that it is basically a simulation of the universe itself. Which inevitably leads to the question, how can we know that we are not living inside this very kind of simulation? Silas Bean and some colleagues at the University of Bonn think they've come up with a way to measure the universe in such a way that we can know if we're living in a giant simulation. This is all based on a value known as the Grisons-at-spin-Kuzmin cutoff, or GZK. In the world of theoretical physics, things can more or less be limitless. But in computers things have to have limits. This is one of the problems with these kinds of simulations. The laws of physics have to be placed in a constrained, 3D space, a lattice, that is limited by the nature of the computer simulation. Bean and his colleagues are exploring whether or not these lattices alter the physical processes we have observed in the universe. Specifically, they are looking at high-energy processes, which get smaller and smaller the more energetic they become. Bean and company have found that these 3D lattices impose a limit on the amount of energy these processes can have, because nothing occurring within the simulation can be smaller than the lattice itself. So, if we are inside of a computer program, there should be a fundamental limit within the spectrum of high-energy particles, like cosmic ray particles. And there is. That's the GZK cutoff. It's well studied and well defined, and occurs because over time and distance cosmic ray particles interact with the cosmic microwave background and lose energy. So, if Bean is correct, we can measure cosmic ray particles using existing technology to see if they behave in the way theoretical physics says they should, or if they behave as we might expect them to in a computer simulation. If we found that the cosmic waves behave in a particular way, we would basically be able to see the construction of the simulation lattice and confirm that we are indeed in a computer simulation. Of course, this exercise only works if the creators of the assumed simulation that is our universe built that simulation the same way we would, which is in fact more probable than not.